Okay, so let's go on to solving exponential equations. And we solved some simple exponential equations where we said if the bases are the same, then the exponents must be equal. But if it's not that simple, we need to use logarithms to solve. And the first step must always be to isolate the exponential function. Always. So let's look at this first example. And I see that I have an exponential function with 4 as the base, and then it's being multiplied by 0.3. So I need to divide both sides by 0.3 in order to isolate the exponential function. So now I have 4 to the 0.2x equals 2/3, and the exponential part is isolated. So now I'm going to use logarithms to solve. And there's more than one way to do this. I'm going to show you always using natural logarithms because you can do natural logarithms easy on your calculator. If you have one of the Casio calculators, it will actually do the logarithm in any base. And so you can do these a little simpler. But I'm going to show you with the natural log. So I'm going to do the natural log of both sides. And notice that the ln comes in the front of both sides. You can't write ln at the back. It doesn't make any sense. And then we're going to use our property that says our exponent can come out in the front as a multiplier and have 0.2x times the ln of 4 equals the ln of 2/3. Then I'm trying to get the x by itself, so I'm going to divide by 0.2 ln of 4 on both sides. So now I have x by itself on the left, and I have the ln of 2/3 over 0.2 ln of 4. Well, I would simplify this a little bit more, because if I have 2/10 in the denominator, let's think about this. Well, that's the same thing as multiplying by 5. So I would write this as 5 ln 2/3 over the ln of 4. And then that cannot be simplified anymore. That's as simple as it gets. And then it says, this is what they want when they say exact form. So this is the exact answer, but still has logarithms in it. And then you're asked to do the decimal approximation. So let's do that. And I'm getting about -3.841 rounded to 3 decimal places. So let me double check that. Oh, now I'm getting something different, so let me do it one more time. Oh, apparently I made an error, not unheard of. And I'm getting -1.462. So let me know if you get something different, because I could be having a bad calculator day. You just never know. Okay, so now let's look at B, where I have 2 different bases, but I can still use natural logarithms no matter what my base is. So I have 2 to the x plus 1 and 5 to the 1 minus 2x. So I'm going to take the natural log of both sides. Ln of 2 to the x plus 1 equals the ln of 5 to the 1 minus 2x. And then I'm going to use my property of logarithms that says if I have an exponent on the argument, I can bring it down in the front as a multiplier. And I need to keep it together in parentheses. And then on the right, we're going to do the same process and have 1 minus 2x in parentheses, comes down in the front and multiplies the ln of 5. Well, now I'm trying to solve for x. I have parentheses, and what I say to myself is if I'm trying to solve for x and I have parentheses, they're in the way. So I need to make them go away by distributing. So I'm going to distribute my ln2 and have x times the ln of 2 plus ln2. And then on the right, I'm going to distribute and get the ln of 5 minus 2x times the ln of 5. So then, if this was x's and numbers, and it is x's and numbers, just ln2 and ln5 are kind of clunky numbers, your goal would be to get everything with an x in it on one side and everything that doesn't have an x on the other side. So we're going to add 2x ln5 to both sides and have x ln2 plus 2x ln5 plus ln2 equals ln5. And then I want that ln2 to be on the other side with the ln5, so I'm going to subtract ln2 from both sides. Then this step is often where students get stuck because they're seeing two x's and they're trying to figure out how to solve for x. So this is the step where you need to factor out an x. So if you're not seeing that, do a lot of practice of this type of problem. And then on the right-hand side, I'm going to simplify that using a property of logarithms to the ln of 5/2. Okay, then I'm also going to simplify my logarithms on the left. And this 2 can come up and be an exponent on the 5. So I'll have the ln of 2 plus the ln of 5 squared equals the ln of 5/2. So on the left, that will combine to the ln of 2 times 25 equals the ln of 5/2. So my final answer, I'm going to divide by the ln of 50, and x equals exactly the ln of 5/2 over the ln of 50, and this is my exact answer. And then my approximate answer to 3 decimal places is 0.234. So let me know if you get something different, but that's what I'm getting for my decimal. Okay, so that was solving this type of exponential equation. Now we need to look at another type, and we're going to revisit that idea again of quadratic in form. So remember, the quadratic in form looks like ax squared plus bx plus c equals 0. So we're trying to see what could be squared to make that first term. So you need to think about, if you have 3 to the x squared, that equals 3 to the 2x. So you need to see that this first term is the second term squared. So if we let w equals 3 to the x, then w squared is going to be 3 to the 2x. And I can write my quadratic in terms of w, so with w's instead of x's. So it's going to look like w squared plus w minus 2 equals 0. Well, that looks like something we know how to solve. If we have w plus 2 times w minus 1, that's going to be the equivalent, but factored. And then we use our zero product property to say w plus 2 is 0 or w minus 1 is 0. So w either equals -2 or 1. So now look for a minute at what we had w equal to. And if we look at w equals -2 and say, does that ever equal 3 to the x? And this never happens. 3 to the x is always greater than 0. If you think about what the graph looks like, it never has a y value of 0. So w can't equal -2. And then let's look at w equal 1. Say, so can 3 to the x equal 1? Well, that could happen, right? So in fact, if you want to see it really clearly, you might take the log base 3 of both sides and bring this x down in front. And then the log base 3 of 3 is 1. And the log base 3 of 1 is 0. So x must equal 0. So you could just see that by inspection here of knowing that the only exponent that's going to work is 3 to the 0 to equal 1. So x equals 0 is our only solution. And if you come back and look at this equation, you can see 3 to the 0 is going to be 1, plus 3 to the 0 is going to be 1, minus 2. Sure enough, that works. Okay, so the next one's a little trickier. We just kind of get a little trickier and a little trickier. So this had exponents of 2x and x. Well, now I see an exponent of an x plus 2. So let me just show you some examples. If I have 3 to the x plus 5, can you see that we can write that as 3 to the x times 3 to the 5? Because the exponents add. And then if we have 4 to the x minus 7, we could write that as 4 to the x times 4 to the -7, because those exponents are going to add. So that gives me an idea of how to rewrite this quadratic looking thing to 2 to the x squared plus 2 to the x times 2 to the 2 minus 12 equals 0. So now I'm seeing that if I let w equal 2 to the x, and then I square both sides, w squared is going to equal 2 to the 2x. And so I can rewrite my original equation as w squared plus 4w minus 12 equals 0. So the 4 is this 2 squared. Okay, and this looks like something we know how to solve. We'll have w plus 6 and w minus 2. And we use our zero product property. So we get either w is -6 or 2. And I think you're getting the idea that if we check w equals -6, and we're asking, does 2 to the x ever equal -6? That we know now the answer to that is this never happens. 2 to the x is always positive, and that's a really useful little factoid that you really want to keep in your close pocket, not in your satchel across the room. Okay. So then let's look at what about w equals 2. And so we have 2 to the x equals 2, and we can see that x equals 1. And you can check that in that original equation and see that it works. Okay, then the last one is very tricky, and I wouldn't put it on a test, but it's a really good practice problem to just get you thinking deeper. So this one I have a 4 to the x and a 4 to the negative x. So I'm not seeing that 4 to the 2x thing. And I sure don't know what to do about that 4 to the negative x. So this is one of those things that I would never think of this myself, but once you've seen it, then you're kind of responsible for knowing about it, okay? So here's what we're going to do. We're going to multiply both sides of this equation by 4 to the x and see what amazing things happen. So I have 4 to the x times 4 to the x, so that's 4 to the x plus x, or 4 to the 2x. Then I have minus 10, and I'm just going to write this out first so you can think about it. And then I have 4 to the x times 4 to the negative x equals 3 times 4 to the x. Well, let's think about this. So that's going to be, 4 to the x plus negative x, right? We add the exponents. Well, x plus negative x is 0, and 4 to the 0 is 1. So this part equals 1. So then these quadratics, we've wanted 0 on one side each time. So I'm going to have 4 to the 2x minus 3 times 4 to the x minus 10 equals 0. And then our substitution could be w equals 4 to the x. So then I'm going to have w squared minus 3w minus 10 equals 0. Factor to w minus 5, w plus 2. Use my zero product property, and w minus 5 is 0, or w plus 2 is 0. So that's going to give me two possibilities. W is 5 or negative 2. So let's look first at, could w equal 5? And that would be 4 to the x. So we need to use the ln to solve this for x. The ln of 5 equals the ln of 4 to the x. The x is going to come down in the front as a multiplier, and I'll have the ln of 5 equals 4 times the ln of 4. Then divide both sides by ln of 4. So x equals the ln of 5 over the ln of 4. And we should check and make sure, but that is a positive number. So that's all we need to know, is that it's positive, because, well, actually it doesn't even need to be positive. Here's our one answer. This is the part where we need something positive. If we have w equals negative 2 equals 4 to the x, we can say that never happens. 4 to the x is always greater than 0. So this is our one answer. And if you notice, this looks like the change of base formula. It's the log, let me write the log. It's the log in base 4 of 5. So if you have one of those cool Calcio calculators, you can do it that way to find the decimal approximation. In this problem, you weren't asked for the decimal approximation. Okay, so now this is just a little example that shows you some of the usefulness of what we're doing. And in calculus, one of the tasks that you will need to do sometimes is find where two graphs intersect each other. One of the things you use calculus for is to find the area between two graphs. And in order to do that, you have to find where their points of intersection are. And we've been learning that the points of intersection happen when the functions are equal. So that's part of what this exercise is about. So first we're being asked to solve, sorry, when I touch the screen, sometimes crazy things happen. Okay, so we want to know how do we figure out what's going on if f of x equals 3? So that's when 3 equals the log base 2 of x plus 3. So this is just a way of saying, why would you ever want to solve a logarithmic equation? Well, this would help you find the value of x that gets you a y value of 3. So we would write this in exponential form. 2 to the power of 3 equals x plus 3. And then subtract 3 from both sides and get 5 equals x. So the point 5, 3 is a point on the graph. When x is 5, then y is 3. So that was A. So then let's look at B, and it says solve g of x is 4. So when is 4 equal to the log base 2 of 3x plus 1? And again, we're going to write it in exponential form. So 2 to the power of 4 equals 3x plus 1. And 2 to the 4 is 16. So when I subtract 1 from each side, I'm going to have 15 equals 3x. And x equals 5. Interesting. So the point 5 comma 4 is a point on the graph of G. So then we're asked to solve, when is f of x equal g of x? And that's how you find points of intersection, right? If you can solve this, then the graphs intersect. If there's no solution, then you can declare that the graphs do not intersect. So let's see if this ever happens. If I have log base 2 of x plus 3 equals log base 2 of 3x plus 1, well, I have logs on both sides with the same bases. So the long ago red box said that means I can equate the arguments. So I'm going to solve for x, subtract x from both sides, subtract 1 from both sides, and x equals 1. So when x equals 1, the graphs intersect. And then we can find the y coordinate of where they intersect by either doing f of 1, which is log base 2 of 1 plus 3, or log base 2 of 4. And you're asking the question, what power do I need to bring 2 to get 4? And that's going to be 2. So the point 1, 2 is the point of intersection. And then the plus and the minus, that's just to remind you that we can find the f plus g function by adding the two functions together. So I have the log base 2 of x plus 3 and the log base 2 of 3x plus 1, and those are added. And so if I want to know what that is, when that is 7, I'm going to say log base 2 of x plus 3 times 3x plus 1. When does that equal 7? And I don't think this has a pretty answer. I think 2 to the 7 equals x plus 3 times 3x plus 1. Oh, actually, I think this one is solvable. So let's see, 2 to the 7, 2, 4, 8, 16, 32, 64, 128 equals 3x squared plus 10x plus 3. So I want 0 on one side. 3x squared plus 10x minus 125 equals 0. And then I've done this problem before. So I'm going to do synthetic division using 5 and see what happens. So I'm going to have 3. 5 times 3 is 15 and add 25. 5 times 25 is 125 and add, and I get 0. So that means x minus 5 is one of my factors. And then I know the other factor has to have a 3x. And then it's plus a 25 because here's my other factor, right? So this would be a bad test problem because it would take a long time to try and find that 5. I've just done the problem before. So I have 3x plus 25 equals 0 or x minus 5 equals 0. Do you think the first one is going to generate anything useful for us? Because you're going to have x equals negative 25 thirds, but then you come back up and look at your original equations and say, oh, if I put negative 25 thirds in there, I'm going to have a negative argument. So f of x is not defined here, so that can't be a solution. So let's see about x equals 5. Well, if I put 5 into this logarithm and 5 into this logarithm, I'm all good. So when x is 5, that's when f plus g of x equals 7. So you would say f plus x g of 5 equals 7. So the 0.57 is on the graph of the two functions added together. Okay, and I bet you can figure out how to do the last one. So happy logarithm and exponential